And our last lecture of this morning is Professor Douglas Galvão. He's from the physics department. He's also participating in our Cepid Center. And he's going to talk about some multi-scale simulations of nanomaterials. Very, very exciting science.
Okay.
Please, thank you, Douglas.
Good morning, and thank you, Mani, for this kind invitation and for the opportunity of showing our work. I'll give you a brief overview of the work at our group in the last 15 years, and examples of using a multi-scale approach to simulate nanomaterial is starting from ab initio up to finite element methodology. Okay. Oh. Okay. Perfect. In the last years, with the development of new software and compute and hardware technology, computers are nowadays just not another tool to help to interpret experimental data, but in itself a tool for discovery. For example, Gleevec, that's a drug that's in the market, was completely concepted from the beginning up to the final stage in silico. So now we have many possibilities of using computer in material science, in particular in nanotechnology. It has been very useful, especially when you have this experiment in theory collaborations. And in particular, nanotechnology has been very active field for simulating materials and creating new tools and protocols in simulation. I will give you some examples of this technology, especially for carbon-based nanomaterials and more recently caucasianides families. Okay. But when you talk about nanotechnology, there is like a saint, and that is Richard Feynman, a very famous physicist, Nobel Prize winner, that at one of the conferences, the American Society, Physics Society, he asked that what will be happen when you have the technology to manipulate or arrange atom by atom. This is now a possibility, and it's almost a synonym of nanotechnology. This phrase is now every time you talk about nanotechnology, sometimes people remember this. There is a plenty of room at the bottom, in the sense that the size, the shape of the materials are very important. Okay. For example, using the same materials, you can change completely the chemical reactivity and also the electronic response, the optical response. You can use as a sensor using the same material. So it's like you do not change the chemistry in a sense that you use the same material, but you have a different chemical response just playing with the size. You change color, so you change electronic property and optical response, and then you change reactivity also. Then you can combine, sometimes in the same device, you can combine the same material with different size and have different sensor capabilities. It's a very, very interesting approach for nanosensors. But the nanotechnology revolution is only possible due to mainly two very special experimental techniques. One is the scanning transmission microscopy. The idea to have a conductive tipping, that then you have tunneling, electronic tunneling, from the tip to the substrate, or from the substrate up to the bottom, to the tip. And the second one is very useful for surface analysis. This is atomic force microscopy. It's a cartoon, but it gives you an idea about how it works. You sense the surface based on the deflection of the tip. So you convert this electrical signal using a software, and you can have very, very beautiful image in colors of this process. Okay, but from the point of view of material science, when you talk about nanotechnology, carbon nanotube, it's a very topic by itself. It was discovered or rediscovered in the 90s by Ijima. And it's, from the topological point of view, it's a very simple structure. It's like having a sheet of graphite. That's called graphene. That's itself a very hot topic nowadays. Then you make this into a cylinder. But carbon, it's a very special atom. And the only one, when you have the same bond from right and left, you can change the chemistry. Only carbon has this large number of possibilities. You can have also silicon, but very few compounds you can do. So playing with this arrangement, you can have the same material, only carbon. You have the same topology, cylinder, but playing with the chiral angle, you can have a completely different response from semiconductor for metallic tubes. And this is in general how to identify semiconductor of metallic carbon nanotubes. In general, you have for every 3, 1 out of them will be a metal, and the other 2 semiconductor. That has been the major problem up to today. After so many years, it's not possible to synthesize carbon nanotube with the same chirality, the same diameter, and the same length that you want. This has been preventing the large use of carbon nanotube in nanoelectronics. But it's still a problem. There are people trying to solve this using molecular synthesis, use molecular crystal, but this has not been successful yet, at least to produce the material in large quantity that can be used in industry. Okay. Why carbon nanotubes are so interesting? It combines in the same material a lot of interesting properties. You have size, it matches the best lithography available, the density matches metals, the tension, that you can literally produce a knot with a nanotube without breaking, while the best steels, you cannot do this many times. If you play at home with your fork, you know that you cannot do this many times before it breaks. In current transport, it's 100 times better than copper that you use now in our wiring. The electronic transmission, it's better than molybdenum that's used in some of these display devices. Heat dissipation, it's twice better than diamond. That's the reference for this. The stability, you can burn your home before you burn the device, carbon nanotube based. The problem is the cost. These are data from 2000, and at that time you would need 150 kilograms of gold to have 1 kilogram of nanotubes. Nowadays, these numbers are better, but still very expensive to buy high quality nanotube, especially single-walled ones. Yeah? So, and also there is the problem I mentioned that you cannot control the chirality, the size, and the diameters. Okay. But for 10 years, people played with the electronic properties. Nobody paid attention to the mechanical properties. So in 2000, this is a very nice work done at Berkeley by the Alex Zettel groups. They used the nanotubes, it's multi-walled carbon nanotubes. They immobilize one side, use a chemical etching to open some of the other tubes by still keeping the inner ones closed, and they use the tip to move back and forth the tubes, and they showed this could work as an oscillator. More important, this could be a high frequency nano-oscillator. The Chinese, a couple of years later, produced some analytical model that confirmed that this could be high frequency oscillators. And there is a need for high frequency oscillator for electronics. Everybody wants playing videos at their smartphones and so on. You cannot do this with the present technology. So you need new approach for high frequency oscillator that could be produced in large scale and at low cost. So we did we did the first molecular dynamic simulation of this process using this. In this audience, I do not need to explain the molecular dynamic tools. You use a universal force field, classical ones, that's like amber or charm. And the simulation tried to mimic the experimental condition. We have two tubes. I keep the external one frozen and apply the force for the inner one and see how it evolves in times. The physics is quite simple. It's almost an experimental realization of the Hooke's law, okay? But it's important that simulation can sometimes provide quite useful insights about the system. For this, in this case, we noticed that it's not any combination of the tube that would produce a sustained oscillator, because if there is some free space here, it doesn't work. This is beyond the experimental capability to distinguish between these ones. This is a sub-angstrom resolution that is not available even for the best electronic microscopes. So in this case, simulation provides useful information about the dynamics of the system. When we did the simulation for the perfect matching, we can see that the sustained oscillation can go for very long times, and also the high frequency. One interesting point, this is not a standard oscillator, because the frequency it's dependent not only on the geometry as the standard oscillator, but when the tube is inside the other, there is no force. So the frequency can be tuned exploiting the geometry. When you do the same simulation with where the coupler is not perfect, you start to have exchange of energy momentum between the tubes, and the oscillation is compromised. Please.
So the outer one is constrained?
It's frozen.
So you
To mimic
it up just because I mean there's no flexibility. I know which is the persistent length of this.
No, that's frozen to mimic the experimental condition when you have many outlayers.
Okay.
So, but in principle, you can have both tubes free to relax. That will compromise a little the oscillation, but it still works.
So in this simulation, you have actually pulled the inner one back and...
No, we just initial velocity.
Okay, just give it a
Yeah.
kick and then it keeps going back.
Because
Between them, pull them back. And
yes, when it's close to here, the van der Waals interaction pull it back. When it's inside, it's the opposite. So it's like a real pendulum.
And there's no force, no
Dissipation.
dissipation,
Almost no dissipation, because there is it's just van der Waals interaction. If you have a perfect matching, the dissipation is very low. Almost forever, but okay. And if you want to create a device, how do we do that? We cannot use as produced, because it's the difference in the diameter that produces the restoring force. We cannot use it open, because in this case, just a single impurity could kill the device. So one possibility is to make this. This doesn't work because of the impurities. This doesn't work either, because there is no difference in diameter, so there is no force. This would be an approach. At that time, fusing two tubes is beyond the experimental capability. Now you can do at the Secret facility here in Campinas. Daniel Ugatti, that's a professor at that department, created a nanomanipulator with three parts. Then you can use the electron beam to fuse the tube. So nowadays it's possible to create this structure, at least at the lab. Of course, to scale it up to industry, it's another question. So this is our proposed system, and let's see it works. It works. So it's protected, and you can control in tune the frequency. One question: how to make contacts with this? That's where the electronic part plays the important role. We can use metallic inside, a semiconductor outer, and use magnetic fields, electric field, microwaves. We can initiate the system without contacts. That's a very, very appealing, because if you have a nanostructure and I need a big contact, you lose most of the advantages. Okay. This paper was in the cover of the PRL. It was on the few works completely done in Brazil to be in the cover.
Yeah, pull it further out.
It's a minor effect, but you're right. You're correct. But as the van der Waals a short-range interaction, that's not very important.
The fact that the tip is fatter means that the interactions are much weaker than the inner part.
That's correct. Okay, so an extended version that was on the cover of Nanotechnology. There is some magazine in Brazil it's FAPESP magazine, also Ciência Hoje, that's the Brazilian Society. So it was a good PR for even the Unicamp exam for undergrads. They adopted this as one of questions, the fix. But for many years, our experimental colleagues joked that, okay, you play at the computer, but in the reality, it's never will work. But some years ago, the Nakayama group in Japan did this experiment. You see, this is a real-time transmission electron microscopy, high resolution. You see the tube going back and forth exactly as predicted by the simulation. So it's a vindication that the molecular dynamic simulation for carbon-based materials are reliable enough so you can use to design some experiments. But going back to the main question, how to solve the problem that you cannot produce nanotubes with the right chirality. One approach would be, instead of producing many of them, just produce a few of them, but very, very long. And on this topology. This is called carbon nanotube serpentines. There are only 3 groups in the world capable of doing these materials. And this is the group that has been producing this. It's only a few groups in the world has this experimental capability to do this. How are they make? The secret is to use a stepped substrate. And the a catalytic nanoparticle is used for producing carbon nanotubes in the standard way. This is a cartoon how you can make this. This is the nanoparticle, the catalytic nanopart. We grow it very fast on a stepped substrate, use a gas flow to pull it forward. It starts to fall, and at nanoscale, the gravity is not important. You never need to consider in your simulation the gravity effect. But in this case, the strong interaction between the nanotube and the substrate, it acts like a gravity. It pulls it down, and it starts reading the substrate. In fact, the serpentine topology is not a nanoscale effect. If you go for a church with very long steps, and you throw a ball with a wire, it will produce the same. This is a mechanical effect at macro scale also. Okay. So we did the simulation. We used the same techniques, but now it's a challenge because we are talking here about 10 million atoms. So it's not an easy simulation. We use this CUDA the graphic CPU units in a cluster, and we run the simulation to see if it works like the experimental guessing. This is a snapshot from the simulation. In this case, most of the atoms are in the substrate. We have about 6 up to 10 million atoms, but most of them are in the substrate. So you see the formation of the serpentine. Very, very nice. One question is how important is the substrate? So we redid the simulation, but using graphite, the graphite substrate. It's not possible to create the substrate. Just to prove the concept that the steps are more important than the material of the substrate. You see the formation, it's almost the same, but the dynamics is different. Let's show the move. The move provides a better idea how it forms. So it's interact with the substrate, it pulls the tube down, it slides a little, but this is silicon oxide substrate, the same that used in the experiment. It's a stick substrate. It stops the sliding until the limit of the elasticity and the kinetic contribution, then it forms. You can control the separation, just increasing the flux of the gas in the experiment. In the simulation, just to increase the applied initial velocities. Doing the same for the No, this is the wrong one. Okay, I add the wrong video. It's supposed to be on the graphite. It's almost the same dynamic, but graphite is not as sticky as the silicon oxide. It slides more, but the dynamic is automatic. We got, again, the cover of the PRL. See, you need to do nice figures so you can compete for the cover. Okay. But one of the few experiments, this was in collaboration with Ernest José Levitt in Israel, and also with Adu Jório in Belo Horizonte. One of the few experiments, instead of producing the serpentine, it showed the tube fall on itself. That was a good, because then you start thinking about, for the carbon nanotube electronics, we have the resistor already done, we have the capacitor already done, diode, transistors, but no inductor. So we start to ask ourselves if this failed experiment could produce the first carbon nanotube inductor. The idea is if it falls on itself, if they could start doing a coil. Then you could make a contact, and then you would have the first nanoinductor from carbon nanotubes. Indeed, they made, but still only few experiments worked, because this is the short circuit between the layers. As this is a very conductive material, so, and they have the same momentum vector, so it start tunneling or start current across the layers. So one way to solve this is to use or double walls. In this case, you have like a real wire that the outer layer would protect the short circuits, or you could functionalize the tube, some of the part of the tube, in order to change the vector momentum to avoid this problem. This is the first nanocoil for nanotubes, but it's still not very effective because of this short circuit.
What about twisting? You just fix one extreme and then twist somehow.
How do you do this?
I don't know.
Because you have no control on the synthesis. No, it's very fast. You did not even see how they form it. They're very fast. So you cannot control. If you could control this, then it would be an easier solution, but it's not possible from the experimental point of view. This is some of the microscope image, you see? They start falling so itself. So we did the same. We run the simulation. Again, it's a very, very expensive simulation. Okay, now this is the wrong film. This is the graphite. You see? Okay, I mix it up. This is the real one. This is the... As José Levitt at Argentina, we had some sound effects. But it's very impressive. The van der Waals interaction is so strong that it helped the cell formation. It dropped on itself and started self-organizing the structure. There are some thermal vibration, but see, it's very resilient. It survives the thermal effect. And it's a very long, the simulation is 1 micron long. We're talking a very, very large simulation. This is from far view, and see the formation here?
What's on top of it? Is it vacuum?
Vacuum. And some elastic wave propagates during the formation. Even in this case, it survives. It's very, very impressive that the van der Waals is so strong to produce the self-organized structures. It was the cover of Nanoletter from last month. And okay, so now going back to the single layer. That's graphene. Graphene, it's nowadays the most hot topic in physics or even material science. Everything you think about graphite, graphene, even relativistic, massless direct electrons, very sophisticated, useless physics, everything people are trying to do or has already done. It was on the first Nobel Prize awards, just six years after the original paper. But again, people are concentrating on the electronic part, but graphene itself is a very amazing material from the mechanical point of view. It's the strongest material to break, even stronger than diamonds if you try to break along this direction. See? In this case, you see the propagation is almost a wave, elastic wave textbook. You see reflection on the border. Okay. Some years ago, the group of Macquarie at Cornell did this very elegant experiment. In this case, they were interested in extracting the elastic constant for graphene. What they did, they create a pit on silicon oxide substrate, fill it with gas, and deposited the graphene membrane. Because the van der Waals interaction is, again, very strong, you do not need contacts. It's a self-sealing system. So they hit the system, measured the deformation, and extracted the elastic constant. We borrowed their ideas to do what we tried to create a sensor for oil or gas leakage. This was in collaboration with the Petrobras, and we are trying to adopt this with Repsol, that's the Spanish oil company. And the idea is stealing their concept, right? We create the tip, the pitch. This is silicon oxide. We deposited the graphene membrane, fill of gas, and heat it up. The question, how is the detachment? If you have a small leakage, not good. But if you have a sudden detachment that you see in the simulation, see, that's very good. Why? Because this can be used as a sensor for gas or oil leakage. And you can use a very simple optical probe to measure the signal. Then you have a very effective, could be used in very harsh environments and low-cost material. We're trying to make this test in the real field.
The experimental results also from a simulation or not?
The experimental results are a different approach, but it's the same idea. We borrowed the idea to use this. They were interested in measure the last constant, now not using as a sensor. We are trying to use as a sensor for it. Okay. Okay. But although you can do this very beautiful simulation with multi-million atoms, there is a serious problem here. You cannot, if you use this standard force field, as we were discussing with Seabra yesterday, you cannot break or create bonds. So you cannot do real chemistry with this force field. Now there is this new generation of they call reactive force fields that allows you to create and break bonds, and they have revolution in simulation now. You can do real chemistry without electrons. You do not need to solve the Schrödinger equation. So if you are interested, of course, if you are interested in the electronic property, no way. But if you are interested in the mechanical property, in fractal, chemical reaction, we can do simulation. The record is from the Chinese Academy of Science for 2 trillion atoms. We are almost in the size of real world. 2 trillion atoms use reactive force field. You can do a lot of chemistry. This is a simulation of an experiment done in the Grimes group. Pedro is one of the authors of this paper. This is a mixed atmosphere of hydrogen and fluorine atoms. We are doing the plasma etching of graphene, as in the experiment. To run this with a quantum method, it will take 10 years perhaps. I can do this in a couple of days now with the Cepid infrastructure. See? They start reacting. The sp2 is being converted into sp3. If you continue with the simulation, you start creating defective areas. If you run this forever, you dissolve the material, exactly as in the experiment. So this is a virtual experiment of plasma etching of graphene that captures very better the chemistry there. And there is no electron in the simulation. Okay. It's very good to start fractal, because in the time scale, and I cannot use a microscope to follow this. It's so fast, and I cannot have control of this. The question is, if I try to break carbon nanotubes, is chirality important or not? So we run the simulation for the armchair, zigzag, and chiral, and you see, for carbon nanotubes, the chirality is still important. The time of breaking, the weight breaking, the pattern of breaking, it's still chirality dependent. If you do this with boron nitride it's a brittle material. So for the boron nitride, the catalytic is not important because it breaks much earlier. So there is no time to the tension to dissipate. It accumulates, it breaks. So in this case, that is not important. It was again a cover of the PCCP. And we can.
The rate is like a symmetry pattern, is a random pattern.
No, it's the pattern. It depends of the armchair or zigzag. In one case, you have very clean cuts. In the other case, you have this random Brahman cut. But in the case of the armchair, you have a very clean cut. And in the experiment, they also see this distinguished. They cannot tell you what tube is which, but they observed clear cuts with random cuts. So, but you can combine carbon with metals. That's important for many kinds of problems. This is a collaboration with Ado Jori in Belo Horizonte. They are using this one problem with gold as a tip. It's gold. It's very soft. We have sometimes the wrong idea because of the jury that the gold it's strong. It's not. That's why you need to add silver or platinum in gold to make it strong enough. But gold, pure gold, it's very soft. So if you use as a tip for scanning, you destroy your tip very, very easily. It's not very expensive, but if you do this for many times, then it becomes a problem. So they are trying to solve how to make better tips. So they come with this idea that to encapsulate the gold tips with carbon nanocones. This is a commercial structure you can buy. There are only 3 companies selling this, but you can do this. It's a almost micro-scale nanocone. So they encapsulate it, and then the tip lasts longer and produce better image. But they want to see why is that? Because the tip becomes much better than they guess it just for the encapsulation. So you run the simulation for this. See, this is the naked gold. You see, it's very easy to deform. Then if I retract the tip, it's almost permanent deformation. You cannot use the tip anymore. But if you use the cone, the nanocone to encapsulate, you see a very interesting phenomenon. It not only protects the tip from the direct contact into the substrate, but more important, and that is the secret why the tip becomes much better. It blocks the slide, the metallic, the slide of the planes, because the topology of the cone fits the tip. So it's like gold starts to behave like platinum. It behaves like a harder metal. That's the secret why the tip becomes so much better. The blocking of the metallic plane sliding that provides this phenomenon. Again, where simulation now only helps to interpret the data, it found an interesting phenomenon that explains the experimental data. Many years ago, we played with this. We are at the time starting to learn how to use this force field. Then we try to shoot a nanotube against a metallic substrate to see what happens. See, because it's so strong, it can go through a metallic substrate easily. Okay, but it is just for fun. We never published this. This was just a learning tool. But chance, many years. Nanocannon. The first nanocannon. By coincidence, many years later, when Pedro was at Houston, and he mentioned in his presentation, we got the same experimental problem from the simulation. Shooting nanotube at very high velocity against, you see how it breaks. So I go fast. Here, Pedro already talked about this. But fractal nanoscale is a very hot topic again. This is a paper published a couple years ago by another group from Rice, where they shoot silicon nanoparticle against graphene layers, and see how it breaks. For their surprise, it's like a bullet into a wall. The fracture is very unique. It only breaks forming these petals. And these petals has very specific angles. The question is why they break, forming these very unique patterns. Again, from the experimental point of view, they cannot follow too fast, and they cannot have enough structural data to follow the process. Only simulation can help to explain this. We start doing the virtual experiment. We are shooting. One of the surprise of the experimental result is the shooting creates a very long deformation, much more than they expected. So we run the first simulation to see if you could capture this effect. You see, beautiful. The simulation. See, the red it's below the plane. Let's run again. I'm shooting. This is the blue. It's the zero, and red it's below zero. So we are deforming below the plane. You see, it propagates very, very far away from a different point of view. See, it propagates very, very far. It's like a meteor impacting the Earth. Okay. Then go to the second part, the real important part. How does it break? Then we shoot again. This is very slow motion, the simulation, so we can follow the deformation. This is a nickel particle shooting at very high velocity, the same range of the experimental one, and we very slow to see how it breaks. Start deforming up the limit, then start breaking bonds.
The graphene sheet is
suspended, yeah, at the edge. You see? The petals appears, and the angles are exactly the same from the experiments. It's amazing how this reactive force field for carbon works so well. We have this is almost an experimental tools for factory, for structures. Okay. But on the other scale, we cannot avoid to do real, very expensive ab initio calculation. But now, one of the problems of this DFT calculation, many of this protection does not work for metal transition structures. Now we have a new generation of these functionals that works quite well. So in this case, we are doing real chemistry now. In this case, I need to solve the Serrano equation, and we start to see if we could explain these experimental data that are very, very strange. And also, this is a very clever idea from the experiments. If you want to dope material, there are in general very few ways to do this. You can do by doping, you can do by chemical functionalization. In this case, that's very clever. Instead of using this approach, that you have to, what's the price to pay? We're starting losing some of the good quality, the electronic properties of the material. For instance, if you functionalize graphene very much, you lose the high velocity of the electrons. In this case, if I start to functionalize very, very much, we start destroying some of the electronic property. You're losing mobility. That is very important for the transistors. In this case, exploiting the lone pairs and levels acid, I can control the tuning of the doping without making very strong deformation. That's no structural deformation, almost no structural deformation. And I can control, I can do a PN junction, I can do solar cells. And you also can explain these very strange structures. This is a new generation of this this new generation of functional, DFT functional. Very good. And now we can treat chalcogenides. That was not possible many years ago. Okay? This is the structure. It was published a couple of months in Nature Nanotechnology. And we are very happy that this paper make it the top 10 of Nature Nanotechnology. We make the top 10. It was one of the most downloaded papers from this year. Okay. And you can also combine ab initio with react force field, as Pedro much, to do this what's called water in powder, because it's a powder that you do. This is a mechanical chemistry. This is a new field when you do chemistry, not heating, but just applying pressure. So the pressure provides the energy to go over the barrier to induce the chemical reaction. Okay, you can go faster. Okay, but now let's go to the real world. This is academic stuff, right? It's important, we publish, but you are talking to make money of this or have a real macro scale application. Nobody wants a nano car, sorry? You want a car with nanomaterials. So what we can do for the real macro wave application with nanomaterials. So we need functional application. That's the first point. They have to be functional, stable, low cost, and live longer than you. Okay? The first generation of this nanomaterial, we call it buck papers. It's the same idea the Chinese make 2,000 years ago. I do it the same way. I compress the material, filter the material. We can do at your kitchen. You can do using. So the girls can do probably better than us. The tools that you use in kitchen, right? It's the same way to make paper, Chinese paper. The only difference, you have to pay $2,000 to buy the nanotubes. Okay. So people did this for a long, long time. And there are many, many applications. Sensors, filters, a lot of stuff you can do with this material. But surprisingly, as Pedro asked the question, we do not know why nobody tried this before. One of the students, this was done in collaboration with Nanotech Dallas, Ray Bugner's group, they started mixing single-wall nanotubes with multi-wall nanotubes. For 10 years, nobody tried this. It was a very simple question. What happens if you mix these two materials? Nobody tried this for 10 years. If when they did this for the first time, they had a very nice results, very interesting results. They observed for the first time a transition from auxetic to non-auxetic materials and back for non-auxetic to auxetic. Just change the content of the mixing. Okay? Okay. If you do not remember with auxetic materials, it's quite simple. In general, when you stretch a material, it becomes thinner along the direction you're stretching. This class of material has this counterintuitive behavior. When you stretch, it expands perpendicular to the direction where you're stretching it. There are very few materials in nature that can do this. But the physics is relatively simple. You can make this with LEGO. You can create mechanical models exploiting these ideas. In fact, there is this Hubble sphere. It's a very popular toy in Europe. In general, young kids become fascinated because it doesn't behave like they expected. You do an operation that it's strange. Okay. You pull it, it expands.
Normal, right?
No. You pull this, that expands. It's like.
I did my shirt, but pull, it expands.
But doesn't increase across the secret's across. Okay. That's better. Let's go back to this model. I'm stretching, it expanding. Right? This is not common. No, very few materials in nature do this. The way to the way to measure this is the Poisson ratio. If the Poisson ratio is negative, the material is auxetic. It's a very simple test to do this. Okay. You see, there are only few materials in nature that are even close to that. One of the most interesting is cork. Cork is probably the only material in nature has zero. What it makes very ideal to use in bottles for wine, because you do not want it to be very difficult to insert, but you do not want to be very difficult to remove. So it has to be close to 0. Only cork has this. It has been very difficult in the winery industry to find a substitute to cork. They mix with polymer, but it's not the same. It changes the porosity as it affects the quality of the wine. So there is no artificial substitute for cork of good quality that could be used. You do not want to use these artificial corks in high quality wines, in very expensive wine, right? Okay. But again, it was a vindication of the simulation because many, many years ago, we predicted for the first time that pure carbon material could be auxetic. This is the only carbon. In red, it's triple bond. This is the polydiacetylene. People were make just a small piece of that. Nobody were capable of doing large crystals. Only few pieces of cross-linked polydiacetylene. But if you forget the details, the topology is the same. So this is the real material, right? It's like cooked spaghetti, overcooked spaghetti. The question is, how can simulate this behavior? It's beyond the best computer in the world. You cannot do this from atomistic. I cannot do this even from coarse grain. It's beyond the capability of this model. So we need to combine atomistic simulation or even coarse grain simulation for a small piece, but we need it in the final to create an analytical model or mechanical model. It took 2 years to do this. This was done by Virto Colucci, that's now a professor in Limeira. Yeah. So you need how to make this. We need to create a simple structural model, but that the physics is not lost. But from the behavior of auxetic materials, we know that the most important contributions are from bending and stretching. Your model has to reliably describe these two features. Okay? Then you do this. We simplify the model. Instead of using this mixed abstractor, I use this approximate model instead of use the wave one straight segments, and doing this and trying the deformation mechanism. After trying in error for 2 years, we got this structure. This structure reproduces the auxetic behavior. We can test this, deriving analytical expression to estimate the Poisson ratio. It predicts the non-auxetic to auxetic behavior. It passed the crucial test. Okay. And most important, I can derive expression that can give me numbers that can be directly compared against the experimental data. So we can help the experimental to improve the behavior. What they should do? They should increase density. They should decrease density, they should increase the length, they should decrease the length. We have the model that predicts the behavior if you do exactly this. So, okay. And when you compare the data, it's amazing that we could create a model that fits quite well the experimental data. It's, again, proving that you can create very, very simple, but still complex enough to capture the major feature of the behavior.
Do you mind going back a little bit? I
Sure.
don't understand what the model is. What are the blue lines? I want to understand how you build the model. What is the model?
The model it's composed of segments that you have freedom to stretch, to bend.
These segments, no atomistic or anything, just segments.
No, we estimate the constant for the atomistic simulation. What should be the constant for bending? The last constant should for the stretching that could produce auxetic behavior. So we create artificial segments, small artificial atoms, molecular dynamic simulation of artificial segments, and we play with the numbers.
What is the material?
That's ideal material, no, not real one. We create new atoms, create segments with these atoms, and then play with the constant in the force field for the stretching, for the bonding, for the inversion, that could produce the auxetic behavior. So playing, and it's a trial and error approach, guiding by more or less, we know the data for the carbon nanotube, we know more or less the range that carbon nanotube should exhibit. Then you use analytical mechanics to derive the expression for the in-plane and for the out-plane, and see if they reproduce the transition, and most important, if you could have numbers that could fit the experimental data. This is the error bar. It's amazing that if you consider the error bar, it's almost perfect. Okay.
There's a blue line across this D, the lower here.
This is out the thickness, so it has to be here. That's the data for the experiments, the thickness. Okay. Okay. And one of the few times that Science make the first page of the Folha de São Paulo, that's one of the major Brazilian newspapers. And the journalist had this catchphrase that the engorda quando estica. Because you pull, it increases along this direction. So it was good. Okay. But you can play with this material to produce many things. Instead of producing papers, I can produce yarns. And how you make this is almost the same. This is the forest. We can now grow very, very good quality nanotube forest. Centimeter square size. And then a very simple, again, like the Chinese make silk. This is the forest, this is Scott tape. I just pull, it comes. If I twist, I can produce the yarns. So I can produce the papers. If I mix them, I can produce the yarns, or I can produce the silk-like structure if I twist, but not very much. Then playing with this is a very, very low density material. See here? It's almost 3% heavier than air. If I drop it, it will take 10 seconds to reach the floor. A very, very low density. It is almost an aerogel. Okay? And this is snapshots how you make the fiber. It's like cotton candy at the circus. I'm old enough, I don't know if you remember this, but at circus, you'd have this from cotton candy that you hit the sugar and start to produce the fiber, then the fiber you have a foam that you eat the foam. It's almost the same approach here. And because if you remember, I mentioned that nanotube, it's the best for heat conduction, right? It's so good that I can produce a Harry Potter cloak device. This is the aerogel into a water. I am applying a voltage. Because the electrical conductivity and the thermal conductivity is so high, it changes it's like the mirage effect. I'm changing the reflection index. It's not the reflection because you're into a liquid, but almost the same idea. So it becomes invisible. So a Harry Potter effect with carbon nanotubes.
Just carbon nanotube then?
Yep. Just carbon nanotube. No metal materials, but just the forest. Just
Forest, you grow nanotubes?
yeah, here.
No, but
Okay,
here,
okay,
I see something
okay.
there.
See here, this is the forest. This is the forest. This is the forest. Here the forest. Each of these is a bundle of nanotubes. I start pulling it here. This is the material. If I cut these materials, place into 2 electrodes, that's that. That's done. It's quite easy to do. No metamaterials needed to produce invisibility effects. Okay. But I can produce the yarns. I take many fibers, again, the same way to produce the fabrics. In fact, they have some pieces of these fluorosensors that look like just a piece of cotton fabric. Okay. You can do this, you can do that, and once I have the material, I can start playing and see what happened. This was a chance discovery. Lima, it's a Brazilian that is there in Dallas. They took the yarns and just insert into liquid paraffin. Then they create a fantastic artificial muscle. A muscle that is 300 stronger than our natural muscles. It can support its weight 10,000 times and produce a lot of work. Why? Because if you remember, the paraffin has a huge thermal transition, about 70 degrees. If you have, this is a simple physics. If you have a twisted system and you have the paraffin inside it, if you expand, there is no way to conserve the angular moment. So the only way is to rotate. So if you do this, it expands and rotates. That's it, physics 101. Okay? Let's see how strong is this. Time. I have half an hour. You see? That's amazing. I have now an artificial muscle that can be photonically activated, could be thermal activated, can be current activated. There are some artificial muscles in the market, but in general, for instance, if you want to use this as a prothetic for handicapped people, you have to carry a battery. So you have few grams for the device and 2 kilograms for the battery. Now, I do not need anymore the battery. I can use light. I can use this, or I can use a small battery.
Tell them what's going on there when the light.
Okay, what I'm doing here, okay.
Is it the light that twists the tube?
I'm using the light. Okay, but this is the pedal, this is the muscle embedded with paraffin. I hit. So,
the person takes a selfie with a flashlight.
Yeah, you can do that. Because you need a very small amount of energy to produce the paraffin transition, the 70 degrees. See? Just light. A very poor light could do this.
Physics 101.
That's why you're in the chemistry now, right? Sorry for the joke.
You have a twisted, elastic thing twisted. It's in paraffin, solid paraffin?
Solid paraffin.
Oh, then it undergoes a phase transition, becomes liquid?
And because it has to expand, and you have this twisted structure, the only way it's to rotate.
Yeah, no, that's high school physics.
Okay.
You mentioned physics. Okay.
Then for fun, we created the first Greco-Roman catapult. Just to give you an idea how strong is this material. This is a few grams of the material. This has some grams of, this is wood. This is my target. See, I turn the voltage on. You see, it's amazing. See how long it was. This is 300 times stronger than our muscles and can cycle millions of times before breaking. It's a real, it was a chance discovery, but anyway. Okay.
So now you're using voltage to...
Yeah, okay. In fact, everything is thermal. But it's better to selling that it's photonic. In reality, it doesn't depend. Because if you shine light, it will hit, it expands. If you pass a current, it hits, it expands. Or can hit it destruct itself, it expands. So in fact, it's a thermal effect. But this thermal effect can be produced by light, current, voltage, or heat itself. Okay. You see how strong it is? Okay. Now you see I can, even a person can move up with this material. Oh, this is here. You see? Just a flash of light. Okay. Very nice. Okay. But about the simulation. How the simulation helped in this project? Well, you see, the structure always form a scroll, a Archimedean scroll. The shape of the yarns. They're always that way. But why is that? Nobody knows for sure. That's where the simulation can help. So what we did, we put a camera inside the material, what is impossible from the experimental point of view, and this camera doesn't affect the simulation because it's just an artificial tools from labs, and I can follow how the cross-section is formed as I twisted the material. You see? And we got the scrolls. I can cut the yarn and compare the cross-section with the cross-section from the simulation. More important, we can follow how the stress has been accumulated and dissipated and how it propagates as we form the yarn. It's a million atom simulation, but you see, if I didn't tell you that this is atomistic, we could think that we are twisting a piece of metal because it's almost the same shape. So the simulation is capturing again the physics of the phenomenon. Okay, so the idea, they gave you this material and tell for the student, play, find good use of this. Then one of one student of our group was doing a sandwich program there, and one of the other guys probably was perhaps playing. I don't know. Nobody remembers how this idea came up, but this is an elastic band, the elastic rod, rubber. They wrap the structures around them, and they start stretching and releasing, stretching and releasing. Do not ask why. That nobody can explain why, but that was again a very good chance discovery. They observe this. After you do this cycle many times, they start to form a self-structured longitudinal. Let's start again. Okay. What they did? This is the rubber. Okay. They stretch the rubber before, wrap the yarns, and release. And start doing this many times. In the end, when they go to the microscopy, they saw this. They have two scale structure. One along this direction. It looks like a crab, right? The external part of a crab that has this structure. And the second structure is inside each one. So we have this macro scale, the second scale. Okay, but this is just a curiosity. The real impressive data is this. Then they start to stretch 1,000% the material, the fiber, and measure the conductivity. You see one of the student Chinese, you see the panda? Okay. So this is like a pacemaker. I'm measuring the pulse, stretching, bending. You can do what you want with this material. The conductivity doesn't change. That says beyond belief if you follow classical theory of conductivity. You cannot stretch copper wire 1,000% and the conductivity doesn't change. That's not possible at macro scale. What is happening here? I can bend, I can stretch, and the conductivity doesn't change. Which is very good for application, especially for medical application, so you can do a lot of stuff where you need to move parts, but you do not want the conductivity to change. There are many possible applications. The question is, how can you explain this? Then Alirio, who is a very smart guy, again, he combined atomistic simulation with finite elements. He created this model. This is a two-phase model. very simple one, when the material has different conductivities, like embedding metal into a polymer, for instance, like a composite, right? And then he started to measure what is the current path. And unbelievable, the matching he got with the experimental data. So it's almost unbelievable that a problem that such complexity could be described that it was a simple method like this. And the secret is like a super percolative state. Doesn't matter what you do, there is already a path the current can follow. And as the current always follow the path of minimal resistance, you can do what you want with the material as long as this path survives. And that was a paper that was published in Science last year and got a lot of attention in the media because of this very strange behavior. Okay.
So, Doris, may interrupt. What is this atomistic combined with?
In the same way like in the other model, try to guess the constant, and then some insights, and you transfer these insights into the finite elements model. It was very good guess.
What the finite element method does for you?
Because you have to play with many parameters until we got the light for the explanation. So we start playing with the density, the paths, the relative amount of the two materials. So in the end, it was a lot of, again, error and trial. But you start for nothing. Nobody could have any guessing to explain this data, especially the experimenter. It was the first time they observed something like this. It's really strange. If you consider for classical physics, you could not explain this. It's impossible to have a macro material do this, it never change the conductivity. It's only possible because of these nanoscale effects. Or we guess right, the explanation is wrong. Could be, but lucky. You need that in science, right? Okay. Then going back again to the classical force field, but at macro scale. I want to explain this very strange behavior. This is a new, this is a rice, they say this is symbol of rice. This is again a chance to discover mixing two very known polymers, PDMS and PVDF. When they mix this, depending the amount of them, they produce these spheres. And this is an adhesive that works underwater. There are very few adhesives that work underwater. It's very good if you are bleeding, so there are many medical applications for this. And this can hold very strange materials. It can hold plastics, organic materials, glass, even metals, and work underwater. Okay. Okay. The question is, how is that? One very strange thing is the formation of these strings. When you compress the material and pull it apart, the detachment is not clean. The detachment always forms these strings. And if you go to the microscopy, the strings are always there. Doesn't matter what you do, the strings are there. So we create a model, and then agora it's multi-million simulation, mixing the two polymers and see what happens. The first thing we saw the formation of the spheres, was very good. Then we tried to press, compress, press, and pull apart. And we got the rings, the strings. Okay. That's the explanation for the paper. I have to go fast, I'm running out of time. Okay. I have 20 minutes to show other things. Okay. This is a pork, this is a chicken, this is paper, this is metal. You see? I can, doesn't fall. Then I can wet this, it still doesn't fall. Okay. This is the simulation. Okay. This is the real material. We got the viscoelastic behavior. And this is what I consider one of the best simulations ever done in polymer science. This is the real tomography. It costs you $5,000 every time you run these experiments. It gives you a tomography like in NMR for people. So you do this in some microscope. With high intense X-ray, you could not do this for a pair. But then you got all the information, the porosity of the polymer, the structure, a lot of information you can extract for the tomography, but it's very expensive to do this. And you have many parameters to adjust. So the simulation could help. You select the best candidates because you run the experiments. Okay. This is our simulation in color that will be directly contrasted against the real tomography. Let's see. This is a virtual experiment. You see? We got, if you forget that we just the scale, perfect. This is done by Gustavo. Gustavo is no longer at our group. He's in California now. Very impressive. Very impressive. We capture the structure of this polymer. Even the porosity we got. Okay. Okay. So in my final time, I have 20 minutes. But even having a lot of smart people working together, in material science, the number of parameters that you can play is huge. So trial and error is not possible. You need to be smarter than this. Then one possibility is to use artificial intelligence to do this. And one of the most successful algorithms is ants. It is bio-inspired and based on the real ants. If you look for the ants outside, you can find a lot of this. Individually, they are very stupid, right? They are blind and stupid. But when you have a colony, they behave smarter than most of the graduate students you have. How is that possible, that individually? So it's like our brain. Each neuron is not very smart in itself. But when you have the colony of neurons, you have a brain. So the idea is to use this principle in computational material science, create algorithms to help you to solve very hard problems, especially optimization problems. Okay. What are these algorithms? First, the real ants, they are blind. They cannot see very far away. But when they move, they use these chemical marks, the pheromone, that create these chemical trails that are the base for the chemical communication among ants. This creates a positive feedback, but most importantly, this creates an autocatalytic process. There are very few processes in nature that combines positive feedback and autocatalytic behavior. Very few. In general, the feedback in economy is always negative and doesn't produce any autocatalytic process. That's the secret of ants. And this was exploited by many computer science, in particular Marco Dorigo, to create this algorithm to solve the optimization problem. There are many different models. We create ours, but the general idea is the same. So the details are different. Okay, and just to give you an idea why this works, suppose you have these ants looking for food from the nest, and they have an obstacle here. So one goes for the long path, the others go for the short path. Assuming that, for simplicity, that the deposition and the evaporation of the chemical marks are the same, when this first ant arrive here, it's already going back, while the other has not arrived yet. On average, there are more chemical markers on this path. And the ants like to go where there are more chemical markers. So the next ant that has to decide to go to this path or to this path will decide to go this, because there are a slight amount of chemical markers. This is the positive feedback. We produce an autocatalytic process. In the end, all the ants are moving in the same. And that's ants do in nature. Okay? Okay. Then we will create our artificial ants to solve some problem for us. Just to give a proof of concept, I want to know, for instance, what is the best conformation of a polymer. Could be a protein, could be a DNA, but just a polymer. And consider just 3 rings. And I will consider just these 2 angles, so just to prove the concept. Very simple problem I can do by hand in a step of 1 degree, right? Even in this case, consider if I do in step of 1 degree, I could make this in smaller steps. But if I consider just 1 degree, I have 360 by 260 for just 3. Consider that a polymeric chain has thousands of atoms. The number of possibilities is larger than the number of atoms in the universe. And I want to ask my ants, give me the best conformation or a good conformation. What's the limitation of this approach? It doesn't provide you the best solution. If you have a problem that only the best solution, it's good for you, this doesn't work. But in general, in technology, in chemistry, in physics, good solutions are good solutions. They can find good solutions. Then you can improve on good solutions. But you have no warranty that they can give you the best solution. That's the limitation of the approach. Okay. So my answer will be with two angles. So I need just two parameters. So my space of solution has only two degrees of freedom. It goes up and down, left and right. Okay. How it works, I randomly distribute my ants in the space of solution. Space of solution is a pair of 2 angles. Each pair of angles is a solution for the possible solution for this problem. So I'm looking for the good conformation, lower energy. Okay? And I can stop my simulation anytime, give an updated for the quality solution, and I can mix the deterministic approach for completely random approach. At the beginning, I use a completely random approach. As I start to have good solution, I change back to the deterministic approach to save computer time. And I can, just to save computer time, I use this taboo condition that it cannot visit the same task sites, the same point twice. But it just saving time. You can, okay. This is my solution.
You have a function for energy.
Right. That's the energy of the conformation of the rotation. This is my space of solution, right? This is my beta angle. This is my alpha angle. They can go for, by symmetry, because I have PP polyparaffin weights, it's symmetrical, so I just need to go to 180. If I change one atom for nitrogen, then I need to go to 360. So they can go from 0 to 180, from 0 to 180. I can do this by hand, so I have this map. This is my map of solution, okay? In red are the best solution. There are 4 equal solutions. Now I let my ants walk into this space. This is a difficult problem for gradient approximation because you have 4 solutions, equal solutions. So sometimes you jump for one solution, the convergence is never reached because you start jumping from one side to the other side. You see, my ants very quickly found all the 4 solutions. Okay, but this is an easy problem.
What was the positive feedback?
The positive feedback is the path. It's the creation of the path. Let's play again. They start moving and create the path. Sometimes, you see, they're coalescence. One ant cross the other path is better than its, then
You have to keep track of the end's path somehow, so that the second end will know, oh,
Right.
A friend of mine was here before.
Right.
Okay.
So that's the path they found. Okay. Just to prove the concept. Let's do in the real problem. I want to design a polymer, a conducting polymer composed of polyaniline units. This is one of the most investigated conducting polymers. It has 3 different units. Depending of the way the relative amount of these units, you can go for insulator to highly conductive material. So now I want my ants to find a solution where I specify the conductive range and the color. How do I measure this? I solve the tight bind Hamiltonian. That gives me the gap and gives me the localization of the wave function. As I'm looking for metallic structure, it needs to satisfy 2 conditions. The gap should be very small, and the localization of the electronic wave function at the Fermi level should be the most spread possible.
When it's plain, actually, you know the answer in some way, because you know that the conducting polymers will be, I mean, the transform will be a polaron, whatever, when it's plain.
Right, but they are plain. But the question is, how I should mix B, C, and A to produce this? The number of possibilities,
Okay.
it's 10 to 23.
Okay.
Yeah. I'm not even considering this, because I'm using tight bind method, so it doesn't matter the geometry. Okay, I'm using the simplest approach. Tight bind, one orbital per site, first neighbors. There is nothing simplest than this. Just, okay.
You can almost solve by hand.
Yes.
Solve by hand, actually.
For each structure you can solve by hand. Yeah, almost. This is solution. I let my ants walk in this space of solution and looking for this solution with these specified parameters. Okay. Yeah. Just a few walks, they found solution already in the literature. Good. They reproduced the data people found before, but more important, they found new solution that has never been tried before. Of course, the number of possibilities is almost infinite, so no chemical could experiment all the possibilities.
So this is the composition.
Composition. This is the solution into the specified parameters, right? They have very small gap and very delocalized structure. So this is a metallic structure.
Did it expire with time? Just like the idea of the chemical that evaporates?
Yes, you can stop the simulation, way up, everybody start again. But you can, that's the good question. That's why this method is so good, because you could use genetic algorithm. But genetic algorithm is stochastic in itself. So it has no memory and no learning capability. This method has memory and learning capability. So I can wipe out my population, but I can keep storage the good solution. So they start for a good solution, try to improve on good solution. So I do not need to run every time everything from scratch. They're very good. See, I can find the solution, just probing very small amount of the space of solution. Okay. Okay, wait back. Okay, sorry. Let's prove the concept. So I invite you to try this with your proteins. It can use evolutionary approach. It can use a database for similar structures, and I guess it will work. But that's not my field. Okay, but can we do? Okay.
So if you want to use, we need some sort of algorithm.
Right, the same algorithm used to measure the energy.
No, I don't. We need like we're doing Monte Carlo. There is an algorithm that you follow. Check this, you do this, check this, you do that. Where can I find the AND algorithm?
No, you have to write itself.
There is some.
Yeah, there are some libraries. There are some libraries available. But doesn't depend on your Hamiltonian. That's the charm of the structure. Yeah. But if you have a very large computer infrastructure, you can storage solution. You can create a library. You can use evolutionary approaches that some of you present here. You can compare structures that are similar. It then can match very, very fast. We tried a different approach. That was a HP. That was a very simple method. But using the genetic algorithm coupled to the maternal effect, where you kill the best in your population, not an elitist approach, you kill the best, we got the best number in the 20 years of literature for the HP. He is writing the paper, but using GA. So it's a very promising for folding. Okay, but can I use this in real world or just playing? Then we have this is very smart undergrad student. He worked here in the Cepid, so he need to do some undergrad project that must be related to his job. So I told him, write these ants for, let's try to find the flood problem in Campinas. Because as Campinas, São Paulo, every time we have heavy rains, there are floods, and people die. This is a third world country. There is no good government to check this. People trash a lot of things in the streets that clogs the sewage and produce problems. So the idea here was, let's get the topology of Campinas from the Google Earth, but a static image, such to prove the concept. Then it is a very simple problem in physics because the water always goes from up to down. So I map Campinas city with this in a matrix that gives the topography and let my ants look for potential problem sites for flooding. I could do this in real time using real data when it's raining. We could buy the real-time data from Google or from some satellite provide. Then I could tell the mayor, this part of the city will be in problem in a couple hours because there are not enough people to go. So, just
check how many votes he got from that region and decided if he wants
that's a good idea. Okay, but let's see how it works. This is Campinas, so you have a free ride to know Campinas. In red are my ants. They start walking around the city looking for potential problem sites. Good, they found the river. River it's a problem because it contains water. So they found the river, that's good. Let's go. And now this is downtown, almost downtown. This is the Guarani Stadium, always flood. Because there is this, you see, a lot of water here also. They found the stadium. That's a site that we know that's a problem. Always is a problem. That's how it goes on. But they found the pool. Good. You see? So this could be a very powerful tool for real application. We just need to have the real data in real time. Then we could project the place that will be flood in a couple of hours or in a couple of minutes. Okay. Okay, just to finish this, sorry it's in Portuguese, but that's why I think that like a Brazilian and a scientist, we should be more concerned about this. Brazil is doing good size. If you go to the metrics, we are doing as good as Russia, India, in number of paper, in number of citation, but we are not doing the same in patents, and we are not generating money, not creating job using our knowledge. We need to do this if you want to be not anymore a third country world. This is an example where you can use the same technology we use to publish a lot of papers in a problem with social impact. This is in collaboration with Rodrigo Bianchi, it's a professor in Ouro Preto. This is the following. The babies in general, this is the most important problem for young babies and very easy to solve in most of the cases. That's the hyperbilirubinemia, blah, 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 blah. That's when they are born, the liver doesn't work properly, so you need to break some of the molecules associated with the liver production. In general, you just need ultraviolet light. So exposing the babies to ultraviolet light, sometime a couple hours, in a few days, that's okay. You solve the problem. If not, you need to use drugs, and use drugs in babies, it's always a medical risk. What's the problem in Brazil? Again, there is no regulation for use the lights. There are no people who use the light until it dies. But the light died much before then its UV spectra is working. So sometimes the doctors think that the therapy is not working, but what is not working is the light, the lamp. Because the lamp is no longer producing the ultraviolet. There is no regulation for this, nobody checking in the hospitals for this. So Rodrigo Bianchi developed a very clever idea using polymers. This is a very common conducting polymer, and it has a very special property. When exposed to UV light, it breaks. And you can create a pattern that the color follows the amount of ultraviolet radiation. So you know if a certain amount of radiation was on the polymer or not. So he created this film to be used in the diapers. So if the baby is under the light, if it doesn't receive the right amount, the polymer doesn't change color. So you know that the lamp is not working properly. Okay? But again, it's a problem of optimization because you have so many parameters for the polymer that you need something like GA or to optimize. What we do, we run these tests to try to optimize these parameters to be used in the best films to be used in the diapers. This is an example of using scientific knowledge to produce a product that has social value. It could generate a lot of money if you have the right environment. On the other part, we are trying to make a lobby with some congressmen to create a regulation that make the hospital to check. So they have a certification for the lab. This is an example we need to do more if you want to create job and wealth from science. If not, you just continue to write papers and theses. That's not important, but that's not the real world, right? We need to do more than write papers. Okay, thank you very much for your attention.
Very nice. Thank you. Questions, more questions before we go eat. Not that we need to after this myself. Questions? Matthias?
So I did have a question on this part of the talk. There are several software using actually swarm technology for exploring, for instance, binding of drugs in buckets, like autodog uses. But the problem is the sampling space. Because if you start considering more flexibility, so if you go to like an alkene chain or something like that, it becomes like intrigue. So how do you think you can really manage going, big scale with your algorithms in particular?
For the perhaps for more complex problems, protein could be a challenge. But for this class of polymer that's always chains, it's not a big deal. You can do it.
Yeah, I mean, point. That's the point. I mean, it's like if you don't use some heuristics for really big, problems like folding that you were saying, I think you cannot really explore the surface enough to get a good result. That's what I'm saying.
Could be, but
I mean, you can do it by chance, actually.
right. Well, if you never try, you never know.
No.
Yeah, our problems are easier because polymers are long chains. So the degree of the sample space, it's less complex than folding. But with GA and HP model, we beat what is best in literature using this maternal effect. So I think there's some room to improvement. So.
Other questions? Have you ever tried this method, something like small fold hammer protein?
No, we never tried. Before, so I like to show this. This is fun. This is how you do science in the third world. It's ours. Brazilians, afraid, not well equipped, not well trained, and you have to compete against the first-class American schools, right? Well motivated, well trained, and well equipped. So,
Full of self-esteem.
yep. So the best solution should be leave the field, right? There is no real competition. But like in life, sometimes you should try because if you are lucky, sometimes you can win. Okay, just a joke.
Can you, the last algorithm that you showed that you said, not the last one, the one with the plus, yes, that one. Can you adapt that to predict like traffic jams?
Yep. The question is we have to the real-time data.
Yeah, but I mean for traffic, I think it's a little bit simpler because the well, at least in big cities, usually have that type of information from
Right.
the cameras, right?
And they can control the traffic signals to slow or increase. They have in São Paulo they use this. They have this engineering advanced stuff trying to use this. But probably the time scale I think probably not worth.
What about
Because you have almost this information in real time. So there is no optimization in this sense. But you could perhaps use to develop strategies to improve flow. That people trying. What's the best model? Should we stop here? Should we stop there? Then you can perhaps use this to simulate. But in the real world, you have access to the data so fast that you do not need simulation just to make the decision what you do.
if this algorithm is, you can make it super fast, you can take, for instance, the real data from waves, for instance, instantaneous real data, let the ants find the most busy place, roads, and you take the complementary space.
Could be.
And add that to waves and tell, well, avoid this, go there, this route. So if the computation if the computation is fast enough, perhaps can be made on the cloud, and so it sends the information back to your cell phone application, saying, well, because usually what the application, well, it tells you, well, this is here is crowded, go there, less crowded. But in São Paulo, maybe the less crowded is still,
It could be. They're using this to train soldiers in war games. In the Afghanistan, they use this. They have the average performance of the Afghan soldiers, the equipment in the Americans, and they play this game to train soldiers. What's the decision? I should move a platoon from here for there. I should move the tanks. They do a lot of simulation because they have the best computer. They do a lot of simulation to develop how to play wars. This has been used in real world for wars. Although the results are not published, of course, but I know from people before the MIT. The MIT is this Institute for Institute for Soldat. For military, there is an institute at MIT for military. An institute for just for using this. They mention that they're playing with this type of game there.
Questions? I have a question before you go to lunch. Very simple. It has nothing to do with this. Suppose you have a polymer. Anything? Just not a question. It's information. If you perhaps try to Google this information. I wanted to know. Let's say I have a polymer, right? And then the polymer has many conformations. And someone comes to me and asks, what is the repeat length? What is this person talking about? What is the repeat length in a polymer? I tried to Google this information.
See, if you are talking about copolymer or polymer?
Well, it could be. I have heard.
If it's a polymer, it's a polymer from the stoichiometric point of view has no meaning. The meaning in this sense is as you have it's a long polymer and you have a distribution of ring rotations.
Yes, okay, yes.
So in this sense, they estimate as a function of temperature, what's the average that one ring in a specific angle will find another or a similar pattern repeat. Yeah, it's more used for copolymers than they have.
Useful, Rodrigo?
Yeah.
Okay.
Kind of optimization procedure like anti-column or genetic algorithm, it's not necessary to know the sensitivity of the problem. You do not use, for example, the derivative of your function with respect of your...
You could use, you could. Doesn't depend on... You can use,
yeah.
Calculate that. Yeah.
And you can calculate other... You can use other methods.
Yeah, the algorithm structure is not Hamiltonian dependent. So it can do what you want as far as you will be able to write an evaluation function. That's the needed. So if you are able to write to translate your problem into an evaluation function, it will work. For sure it will work.
In this case, you can use the most efficient optimization problem.
Yeah, a lot of people from different fields perhaps could benefit trying this because it has been very confined in people from optimization problem. Now people start to use in material science, but it's more computer people doing optimization calculations.
I want to try something here.
No questions? Thank you very much.